All right, so here's a problem. That's a cantilever beam. Has a uniform load for half of it and then a point load down here at the end. And we'll determine the slope and displacement at the free end. We can do a lot of different techniques. We could probably do this with direct integration. We talked about that earlier. We could probably do this with conjugate beam, but I want to try this with virtual work. So the first thing we need to think about is, remember virtual work, we need the expressions for the moments in this beam. And then we're going to do the virtual system, and the virtual system will have a load at C, and if we're going to do the slope, which we will, a unit couple at C. There's probably an advantage to thinking about your coordinate system. Normally we like to start here on the left and go to the right, and we could easily do that and write two equations for moment, one that would be good from 0 to 7, and a second that would be good from 7 to 14. So we'd have two real, or two moment equations for the real load. And then of course if you imagine all those loads removed and just a single load out here at C for the virtual load, we could write one equation for the whole section. So it may not be as bad as it seems. Now if we do start from the left and work to the right, we'll need to find these reactions at the fixed connection. So what I'm going to propose today, just as a change of pace, is let's choose different coordinate systems. So I'm going to choose a coordinate system that starts on the right and goes to the left. So what would be the main advantage of that coordinate system? I would not need the reactions at A. That can save yourself a little time. So think about that. If I were to define my coordinate system from right to left, then when I cut my system here to try to find the moment in this section from C to B, the most likely candidate would be to look to the right. That would be a pretty simple free body to deal with. And then when I got over here and I made the cut somewhere between A and B, again the most likely candidate would be looking at the right hand side. So I'd never have to worry about my reactions at A. A little specialized solution, but taking advantage of the fact that this is a cantilever and I don't necessarily need these reactions. So with that as a background, let's go ahead and see if we can develop these moment expressions. So I'll start with this one here first. So this would actually be the segment from X going from 0 to 7. And if I draw that free body at some distance X, I don't have any reactions. Remember, the only thing I'm looking for is the internal moment. So there's the moment. I did leave off my load here at the end, which is 75 kilonewtons. Okay, so if I sum the moments at the cut and make sure I'm in equilibrium, I can find my internal moment. So with right-hand rules, my sign convention, my internal moment is positive or negative? Negative. And the moment about the cut produced by this 75 kilonewton force is positive or negative? Negative. So the force, 75 kilonewtons, times the distance, x. So it looks like my moment there is just minus 75x. And the units would be in kilonewton meters. That wasn't so bad. Any questions about that? All right, so keeping the same coordinate system, let's look at the second section. So this would be the section from 7 to 14. So that free body looks a little bit different. I still have my 75 kilonewton force here at the end, and then I have a portion of the distributed load, and that, as you can see, has an intensity of 25 kilonewtons per meter. This is still my distance x, but I know this part is 7 meters, so what would this little segment be? Be x minus 7. And then I'm still looking for the internal moment, m. So the first thing I want to do is find this concentrated equivalent force. So I'll just call it F. So F is going to be the area under this part of the curve. It's a rectangle, base times height, so it will be 25 times x minus 7. You guys see that? And what is the distance? Oops, I went the wrong way. What is the distance? I'll call it D. What is the distance to that force from the cut? Right, x minus 7 over 2. I'll just put the 1/2 out in front. So now I can sum my moments at the cut equal to 0, equilibrium. And let's see what we've got. So starting here at the left side, I've got the moment, which is, as we talked before, is negative. The concentrated equivalent of this distributed section is also creating negative. So it's going to be this force times this distance. So it looks like I've got 25 divided by 2, and then x minus 7 squared. And then finally, way out here, I've got the concentrated force 75 times x. So my real moment in this section would be, just throw all the stuff to the other side. I get minus 25 over 2 x minus 7 squared minus 75x. And that has the units of kilonewton meters. So not horrible. We might expand this later. When you expand this term, obviously you'll get some x terms, and you can maybe cancel or combine that together. Let us hold it for it right now. So any questions about that? So we're about a third of the way through. I think what I'll do for this example, since we've done some displacement calculations before, is let's start with the slope. Okay, so if I want the slope, what do I need to do? I need to take this geometry and apply a unit couple out here at the end. So my virtual beam for the slope is going to look like this. Still a cantilever, fixed on the left edge. Okay, now let's think about this. This point C, under this loading condition, do you think it's going to move up or down? Probably down, right? And as it moves down, I wouldn't be at all surprised if the deflection had some shape like this. So what do you think this slope at C is going to be? Positive or negative? Negative. So what I'm going to do is I'm going to assume a moment that's going to create a positive slope on the end. Then I'll probably get what? A negative result. So my negative will match this negative. So by assuming a positive moment, if you look at this virtual beam, how would you expect it to displace? Probably like this. And that's how it generates this positive slope. Now when I do my calculations, if I get a positive answer, then I assume correctly. If I get a negative answer, then I assume wrong, which means I should get the negative result. So I'm kind of always going to assume a scenario that will produce the positive quantity. That way my result will, the sign, I won't have to go back and change my signs or change my direction. Now how many virtual moment equations do I have to write for this structure? Just one. So I'm going to, this equation will be good for the entire 14 meters. This thing is 14 meters long. So if I make that cut, remember I have my moment. Oh, also in the way we're doing this, this has a very strange unit of meters. The force is dimensionless, but it still has force times a distance, so it has a strange unit. So now internally, I have the lowercase m, or the virtual moment, at my distance x. So if I sum moments at the cut, set it equal to 0, what do I get? Well, internally this moment is negative, and this moment is positive. So my virtual moment is simply 1. That's pretty handy, right? Because remember, when we write our virtual work equation, what do? We make the product of the real moment times the virtual moment. And if our virtual moment just happens to be 1, that's a pretty easy product to form. So now I just need to multiply this times the real moment divided by EI and integrate from 0 to 7. And then multiply the virtual moment times this real moment and integrate it from 7 to 14. So my virtual equation for the slope at C, I'm going to go ahead and keep my 1 over EI out as a constant. So I'll be left with the integral from 0 to 7 of my real moment times the virtual moment, which is just, I lost the sign, negative 75x dx. Does that look right? And then plus the integral from 7 to 14 of the real moment times the virtual moment, which is minus 25 over 2 x minus 7 squared minus 75 x dx, and then we'll close up our bracket. So if we were doing this on the exam, this is where you could stop. I think given enough time, you could probably do these integrations and evaluations and produce a numerical value. That seem reasonable? I think what I'll do is not take up a lot of class time on that, but I'll go ahead and do the displacement component, and then on the second page I'll sit down at my desk later today and I'll finish this up and provide you a numerical solution. But I think as far as demonstrating the technique for class, this is good enough to stop here. And that would be good enough for me on the exam. Like I said, I think at this point in your engineering career, these are pretty easy integrals to do, and just a little algebra and some simple calculations, and 10 minutes later you'd have an answer. And for me, that's kind of a wasted 10 minutes in the exam. So I'll just go ahead and put my line underneath that and say that's good enough for me right now for that answer. But again, it won't be in the video, but when I post the PDF of this solution, I'll go ahead and work it out. So let's do the displacement. So if I'm looking for the displacement at C, what does that virtual beam look like? Well, it's the same beam. Geometry is unchanged. Except now I'm going to assume that it has a unit of 1 down. How many equations do I have to write for that? Again, 1. So I just can go from 0 to 14. Here's my free body diagram for this. Oh, I just noticed or just realized I made a notation error. This should be little m theta. That's what we've been talking about in class. Remember that? To distinguish this virtual moment from this one. I used the subscript theta to indicate that that was a rotation. Theta is usually, we usually use theta for angle, and that would imply the slope. It didn't show up in this expression, but I went ahead and make that change. And then we can come back here and sum the moments at the cut. Make sure it's in equilibrium. Again, I have my virtual moment, and then minus basically 1 times x, which is x. So the virtual moment is simply minus x. I guess technically up in this expression I would also subscript that theta and that theta. So now all I have to do is, instead of multiplying for the slope, I just multiplied 1 times everything. For the displacement, it's going to look very similar, except I'm going to multiply by negative x. So now let me draw a little squiggly line here to break that up. So my displacement at C will now be 1 over EI. And the first segment of the structure from 0 to 7 will be negative 75x times negative x, or positive 75x squared dx. And then plus the integral from 7 to 14. And again, negative x comes into here. I'll just run that through again. So I've got, let's see, that'll be 25x over 2. I still have my x minus 7 squared, and that would be plus 75x squared. And that's dx, and close up the bracket. So again, that's not super challenging to do. You do have to take your time. This is a little tedious to expand this and generate the 3 terms, collect it. But it's still just a polynomial. It should be fairly easy to do given enough time. But again, my feeling is that's just grinding it out. And if you can write this, you've done all the hard work. You've conceptualized the problem into a virtual work problem. You've been able to write moment expressions, not once, not twice, but 3 times, and then combine them in the appropriate way, integrate them over the right distances, and there you go. So any questions about that? Again, I will on a second page. I'll go ahead and complete these and give you the result. But for me, that's good enough. Now, I know for mastering engineering, that's not good enough, right? You have to go ahead and finish the whole thing. And I do want you to look at it, because these units are going to be a little tricky. Remember, a gigapascal, a giga is a billion, 10 to the 9th. And remember, a pascal is a Newton per meter squared. And everything else is in kilonewtons, so don't forget that. There's 1,000 of those. And also, when you convert this millimeter to meters, that's going to generate a 10 to the 12th conversion. So just make sure all that works out nicely. And more than likely, too, your answer will end up being in millimeters. Unless you want it in meters. It's up to you, however you want to do it. I'm not sure. Does mastering engineering ask for, do they give you a value? Do they give you a unit? Like if they say meters or millimeters?
Yeah.
Okay. On the exam, I wouldn't care as long as you tell me meters or millimeters. I don't prefer a unit. So any other questions before we stop?
Will we have to have units for the equation too?
I have not. I've left them off, but you should. I tried to carry my units through this equation, right? The moments are kilonewton meters. I got sloppy up here. Well, I didn't. That's a meter. This one I left off. This one should have been, this is also in meters, the units. So if you look at this unit right here, it's kilonewton meters, and you're going to integrate in a meter, so you're going to get kilonewton meters squared, and then when you divide it by EI, they cancel. This will end up being a dimensionless quantity.
So I thought you multiplied it by that 1 meter. So wouldn't it be kilonewton meters squared?
Oh, it would be kilonewton meters cubed when you're done because of the dx. You're right. So it is. The 75x is kilonewton meters times the virtual load is meters. So you get kilonewton meters squared. And you integrate that, you get kilonewton meters cubed. Is that right? No, that's not right. I did something wrong. What did I do wrong? What did I do wrong? I guess what I made the error on is maybe this thing is dimensionless too. So this would have no meter. When you got here, you'd have kilonewton meter integrated, kilonewton meters squared. That works out. Yeah, so I got sloppy with my units. It works out fine down here because right here you have kilonewton meters squared, and then you integrate it, you get kilonewton meters cubed. And when you divide by EI, you should be left with length. So this should be dimensionless. The way I'm doing it. Sorry about that. Okay. I'll go ahead and stop this.
And why did you say?
Another question?
Why did you say the dimensions?
Sorry, say again?
No, why did you say for the slope? Why did you say it was dimensionless?
Well, we make it dimensionless here because it's virtual. It doesn't really exist. So the same thing is here. And what I did up here is I just assumed the force part was not really there, but the meter part was there, and that's not right because the units don't work out. You remember from our previous discussion that the numerator of all of our slope terms are always kilonewton meters squared or force length squared. And if this thing had a meter unit, then you would have kilonewton meters squared integrated with kilonewton meters cubed, and that wouldn't work out. So the way we're going to work it in our class is all the virtual load and the virtual couples are dimensionless. That's a good discussion. All right.